This video is all about translating motion graphs, going from position to velocity to acceleration time graphs and all the way back. So when we're talking about accelerated motion, when we run into curved position versus time graphs, the same general ideas apply to when we have just nice constant angled lines. So when we're trying to go from a position graph to a velocity graph, we need to find the slope of that line. So the slope of your position graph will tell you your velocity. The slope of your velocity graph will tell you the acceleration. Now the same thing applies here, but since we have curves, we have to go about it a little bit different way. So we have an example here. Let's say we collect some motion data and we come up with a position time graph that looks like this. So what we need to do is we need to figure out how do we turn this into a velocity versus time graph, and how do we turn that into an acceleration versus time graph, excuse me. So let's go through some general tips on how to kind of go through that process. So as I look at my position versus time graph, I don't know the slope of that line because there's a lot of different slopes, right? Because it's a curve, I could look at the slope right here, or right here, or right here, and it looks like it's changing. And that's really important because it tells us that the velocity is changing as we go through the motion. So the trick to solving a problem like this is to use tangent lines. Now a tangent line is essentially a line drawn where the line itself does not go through the graph, but it touches the graph at only one point. So you're kind of getting what is the slope at that one tiny point. So to kind of put it into perspective, what I like to do is I will draw some tangent lines in there. So I'm going to line up my ruler just like this, where it's only touching one point on my line. And I'm going to draw a little tangent line through there. Boom. So there's a tangent line. I'm going to pick another point, say maybe this guy right here for my second tangent line, and then maybe pick a third one over here. And that gives us a nice visual of what's happening to the velocity as time is going on, because it looks like, in this case, because I have a really, really steep slope, that means I have a high velocity, and my velocity is getting more and more shallow, which means my speed is dropping. It's getting slower. So to help me build my velocity versus time graph, I'm going to ask myself two questions. Number one, is this positive or negative? And if I look at my slope, all of my slopes are negative. So I'm going to circle that one, and we'll come back to that. And is it speeding up or slowing down? Because that's going to help us with our acceleration versus time graph. And I look at this and I see that my slope is getting more and more shallow, which means that we are slowing down. So in our case, we are slowing down in the negative direction. Now let's talk about how to do our velocity versus time graph. So first things first, I need to figure out, am I going to be in the negative section of my graph or in the positive section of my graph? And based on what I wrote up here, because my slopes are negative, I'm going to be hanging out in that bottom portion of the graph. So all of my data points should be in the negative zone. And all that means is the direction is negative. So it's telling me I'm slowing down. My velocity is decreasing. So I must have gone from a high velocity, a high slope, and it's getting closer and closer and closer to zero. So what I can do is I can say, okay, I must have started with a high negative velocity, and I'm approaching zero. So I can draw it something like this. Because it's negative and it's slowing down. So the closer you get to that 0 point, the slower you go. Now, just like we went from position to velocity by finding the slope, we can do the same thing with our acceleration. So what I need to do here is I can ask myself again, is my slope positive or negative? And it looks like even though I'm in the negative portion of my graph, my slope is positive. My slope is going up. So I have a positive slope. So for my acceleration graph, since we have a nice constant positive slope, my acceleration should look something like that. So notice how when we're talking about positive and negative, the only thing we mean is direction. Just because we are slowing down does not mean that we have a negative acceleration. It's only positive and negative. Now, for slowing down, notice how we have a negative slope for position and a positive slope for velocity. So those two are kind of fighting against each other. That's why we are slowing down even though we have a positive acceleration. Now let's try an example of translating these motion graphs. Now instead of going from position to velocity to acceleration, we're going to start smack dab in the middle. So here we are given a velocity versus time graph. So we have Scooby-Doo that's running at a nice constant speed, and then when he notices there's a second monster, he's going to slow down to 0 within that 9 seconds. So what I would like you to do in your notebook real quick, see if you can sketch out without any numbers what an acceleration versus time graph would look like for these two chunks of the motion, and what would a position versus time graph look like for this chunk of the motion. So let's check your answers in the Scooby-Doo case. So we have our velocity versus time graph here. And it looks like we have a nice constant velocity, so it still looks like they're moving for that period of time. And then it looks like they are slowing down in the positive direction. So maybe let's start by going from velocity to acceleration, since that's what we probably feel the most comfortable with. So if I'm going from velocity to acceleration, I know that the slope of velocity is my acceleration graph. So as I look at this horizontal line, it's telling me that I have a slope of 0, which means I have an acceleration of 0. So it doesn't mean we're not moving, it just means we're not changing speed. Now for the second portion, we have a negative slope going on in the positive direction. So if I were to go from velocity to acceleration, since the slope is negative, that must mean my acceleration is negative as well. Now that's not too bad. The hard part is how do we go from velocity to position, because that's not normally the order that we do things. So let's kind of think about it. In this first case, we have a nice constant speed, and we've dealt with this before. For a constant velocity graph, we know that the slope of our position graph is the same as our velocity graph. So we must have a constant positive slope. So let's draw that. Let's say we are starting from 0, doesn't really matter, but we have a nice constant positive slope. Now for the other piece, when we're accelerating, we notice that the velocity is still positive, so all of my tangent lines should still be going in the positive value, but it's decreasing. So when I draw my tangent lines, I'm going to draw positive slopes that are getting more and more shallow as we go. So if we think about it in terms of a tangent line, you can kind of sketch it out like it's going faster and it's slowing down more and more and more. So if we were to turn that back into a smooth curve, it might look something like this. So notice how when we have a constant velocity model, we have a nice straight line for our position time graph. When we have acceleration in the mix, that is where we get that curved line, and we need to use our tangent lines in order to correctly solve that.